Good morning, all of you. I'm Apala, and I'm from the Department of Electrical Engineering, IIT Kanpur. I'm working with my supervisor, Professor Mohammad Jaleel Akhtar, and my presentation today is on Chipless RFID tag using quad bridge complementary split-ring resonator. So to start with, we'll briefly go through the outline, which states about the introduction, background, the designing of CSRR, how we have modified into our proposed structure, what is the difference between a conventional CSRR, a co-directional CSRR, then followed by RFID tag and field analysis, data encoding concept and conclusion. We won't be showing much of the sensing applications here because it has been widely shown from quite a few presentations. So we'll briefly and in depth go into the design concepts and analytical part. So to introduce, the full form of RFID basically stands for radio frequency identification, which basically means the reading and writing of data using RF signals and to determine specific objects or certain objects at certain locations. Now using RFID, certain frequency band allocations can be done in the electromagnetic spectrum, and as like other sensing applications, it can also be used for a wide variety of applications starting from healthcare, control automation, industrial applications, signal processing and all. Now, recently, different kinds of RFIDs have come into play, unlike the conventional RFIDs, which are the chipless RFIDs, which has their advantages in terms of design simplicity, miniaturization, robust, and cost effectiveness. And the very critical aspect is that these RFIDs do not require an additional miniaturized, external integrated circuit board or any ASIC implementation. So this is one of the critical or the major advantages for chipless RFIDs. Now, data encoding using chipless RFIDs follows the basic concepts of TDR like time domain reflectometry, amplitude and phase modulation using backscatter phenomenon, or frequency domain, which is one of the most popular. Now, frequency domain can be categorized into LC resonant techniques, which is a very narrow band and accurate resonant techniques, and they have their forms in terms of metamaterial inspired resonance structures like split ring resonator, which we commonly called as SRR, or complementary split ring resonator, CSRR, spur line resonator, C-type resonator, open slot resonators, and so on. And it is very essential to form or design this LC resonant circuits or techniques into their planar form in order to achieve more compactness and ease of integration with other RF components and microwave circuits. So if we go into the background, we'll see some of the basic visualizations of these LC resonance circuits. So the first one is a split wheel resonator. This is established based upon its electric field confinement, and this is usually capable of encoding 2 to the power n-1 terms of items. The second is a spur line resonator. Is also capable of tagging 8-bit of data allocation to it. And by increasing the number of spur lines, the number of data allocation and the number of bits can be increased. Now, apart from these two, recently these metamaterial inspired resonators have also been coming to play for the designing of chipless RFIDs, which are flexible SRR, split ring resonators, or CSRR, complementary split ring resonators. And they have an additional degree of freedom where upon increasing the number of rings, so whether on the same plane in case of SRR or on the different plane in case of CSRR, the number of bits or the number of frequency allocation to respect to each bit can be improved. And now they are also essentially modeled into flexible substrates like PET, polyethylene tetraphthalate substrate, or plastic substrates in order to achieve high performance and high flexibility in terms of their application. So recently, a very interesting concept, which is the hexagonal CSRR, has come into play. Here, the split rings, as you can see, are etched on the ground plane into hexagonal patterns. And here, each resonant ring is capable of encoding 2 bits of information. So there are 4 rings and it's capable of encoding 8 bits of information in total. So this has led to the development of our concept, which is a co-directional CSRR, where the frequency allocation improvement is shown only using 2 bits of information. And obviously, by increasing the number of rings, the bit allocation could be improved. So what is complementary split ring resonator? It's basically we can say the mirror image of a split ring resonator that is developed in terms of Babinet principles, and it is excited by using the most popular microstrip line where if we incident an RF signal from one port, the axial component of the electric field becomes perpendicular from the top plane and gets confined to the bottom plane, where it excites the complementary structure that has been etched. Now, for sensing application, if any perturbation in the electric field takes place, we'll be able to achieve the sensing accordingly. And in figure A, we'll see a conventional CSRR where the splits are on the orthogonal ends or on the opposite side. So these can enable us in achieving a single resonance. However, if they are made co-directional or the splits are at the same direction, then we'll be achieving two resonance instead of one. We'll see how in the coming slides. And the frequency of resonance is given using the formula 1 by 2 pi root over of LC where the the in-depth equations are shown here. Here, NOC is basically the number of slots in the split rings. L slot is basically the diameter of the inner ring. And there are two additional terms, WD, where W is the width of the metallic microstrip patch, and D is the distance between the two slots. And an additional factor which we are calling as the filling factor, that has been shown by equation 6. And here, since we are saying that in co-directional CSRR, why two resonances are coming into play, we'll briefly say that if you see the equivalent circuit, here are two resonant LC tank circuits instead of one, that is playing one of the major role for getting the two resonances. The EM part will be seen later. So I'm sorry about the formatting part. So first we have designed a conventional co-directional complementary split ring resonator as we are seeing in the figure. So this is a simple CSRR that has been made co-directional, where the splits are on the one side and the excitation is done using the microstrip line. The resonant frequency are obtained at 5 GHz and 7 GHz, as I said, that for co-directional will be obtaining two resonances instead of one. And what we will be able to achieve is that by varying the split gaps in the CSRRs, the resonant frequency shift will take place. So this resonant frequency shift is not because of the perturbation, but because of another analysis that we'll be studying. And we will see that for the outer ring split gap variation, we have almost around 600 to 700 megahertz of band allocation. And for the inner ring, there is around 600 megahertz of band allocation. Now for the modified quad complementary split ring resonator, here we have modified the microstrip line into a quad bridge kind of a structure. And instead of the circular CSRR, we have made a rectangular co-directional CSRR in the ground plane. And so what happens is that this is giving an improved performance. So because instead of the axial electric field that is exciting the CSRR, since the CSRR is oriented along a specified direction on the left-hand side with respect to me, there will be a time-varying electric field and magnetic field coming into place, as well as due to the etches in the quad design, there are fringing electric fields that will also be coming into play. So the combined action of all this electric field is basically coupling or exciting the sensor or the resonator in such a way that we are getting an improved bandwidth allocation of 600 megahertz for the first resonance and 800 megahertz for the second resonance. Also, very important thing is that when we design the conventional structure, we kept the split ring variation to be exact. We just changed the modified microstrip structure, and only by modifying the feed line and improved bandwidth allocation was obtained. Now, as I said that why we are getting the second resonance for a co-directional CSRR. So if we see the first structure, this is a simple conventional orthogonal split CSRR that has been made. And the fundamental resonance is somewhat around 3.8 gigahertz, and the second harmonic is around 7.6. But if we see the co-directional CSRR, we'll observe that the first resonance is somewhat splitted into double resonances. So this basically happens because when we will observe the surface current distribution in the structures, there will be a change in the co-directional CSRR, somewhat elongated and different as compared to the conventional structure. So this is basically ascertaining the fact that instead of a single resonance, we are getting dual band resonance using just a mere variation of our ring area. So for our design, the L effective length and the frequency has been taken into for designing our structure. And the first response gives basically the split variation responses for the first resonance and the second resonance for the conventional structure. And the next one is for our modified structure, where we have improved band allocation of 200 megahertz for beats for each beat. And this is the E-field plot for the quad B structure. We will see that for the second resonance, since we are getting the resonance shift for the inner ring, so the maximum field confinement is within the inner ring area, and for the first resonance, it is in the outer ring area. So one thing I missed that why is this frequency shift taking place in a particular direction? This is because when we are varying the split gap, say from 0.2 mm to 0.4 mm and so on. So this is basically increasing the inductive or the metallic region, which is giving the more current, more circulating path to the current. So as the circulating path for the current increases, the inductance in the region increases. As inductance will increase, the frequency will gradually shift to the lower side. And then finally, to encode the concept of data encoding, the two resonances are obtained at 5.78 gigahertz and 6.48 gigahertz, giving us four different types of combinations that could be encoded from 00 to up to 11. And a brief comparison in the literature also suggests that just by using 2 bits of information, an improved frequency allocation of 200 megahertz can be obtained. Obviously, if we go on increasing the number of rings in our structure, number of bits will subsequently increase as 2 to the power n. Now, before we go into the conclusion, I want to say that we have not yet fabricated the structure, because fabrication, we can easily do it using Rogers or FR4 substrate in our laboratories, and then we can show the split variation by using copper tubes. But this is not a very reusability or a robust technique that can be used for the application. So what we are trying to develop is make these flexible structures and then excite using some standalone sources or antenna sources, so that when this will be placed on the object of our choice, upon impinging of an electromagnetic signal, we can get the information from there, and then we can make a setup for using this flexible Chipless RFID. So to conclude, we'll say that our design has been formulated at 5.78 gigahertz and 6.43 gigahertz, and an improved frequency allocation of 200 megahertz can be obtained using only 2 bits of data. As I said, that the coupling and the optimum design configuration helps in obtaining our results in a more effective way and confining the electric field in a more specified manner. Thank you so much.